Welcome to EPG Pathshala in Computer Science. So this is again a series of lectures in computer networks, and today's topic for us will be MPLS, which is multi-protocol label switching protocol. So multi-protocol label switching is what we will be looking at. So we will first look at what is meant by this multi-protocol label switching, the idea, then we will look at the architecture of this protocol, details of the protocol. Okay, this is what we will look at. So when we talk of switching techniques, right, we are very familiar with circuit switching, packet switching and virtual circuit switching. So what is this label switching? So that is the first question that comes to mind. So we know that in circuit switching a path is set up beforehand and then data is just sent down that particular path that has already been set up. In packet switching, every packet is treated as a new packet that is coming in, which comes with all the complete destination address and so on, and every packet is routed, right. Every packet you look at the address, and based on the address, hop by hop we keep forwarding it. So that is in packet switching. In virtual circuit switching, we know that we try to get the advantage of both circuit switching and packet switching by setting up what is called as a virtual circuit. It is not a physical circuit, but a virtual circuit that is set up with the necessary entry so that this forwarding at each of the routers can happen very quickly. So in label switching also, we use an approach which is very similar to that of virtual circuit switching. Okay, so only thing is now we assign what are called as labels, and we use this label as the means for doing the switching. So which is why it is called as label switching. So in a sense, it is very similar to virtual circuit switching also. Okay. So what is the motivation for this new protocol called the it is not a new protocol, but compared to IP, this is a protocol that has come in later, right. So compared to IP, why is it that an MPLS kind of a protocol was first of all proposed? So to understand that, we need to understand the disadvantages of the IP routing mechanism. So if in IP as such, if you look at the IP protocol itself, it is a connectionless protocol. Okay. So it does not directly have any support for quality of service, and each router will have to make its own independent forwarding decision based on the IP address, which makes the whole process slow. And remember, the IP headers are pretty large, that is at least 20 bytes of header will be, the standard header itself is 20 bytes, which needs to be processed at every router. Okay. And we are doing this routing at the network layer rather than just a simple switching. So it can be slower than the switching process compared to circuit or virtual circuit switching, right. So it is a slower process, and usually IP is designed to work with the shortest path routes, right. You basically work for shortest path. You normally do not take into account additional metrics. So we would also like to take into account additional metrics wherever possible. Okay. Now the requirement for QoS, the requirement of faster processing, all these things have come about because we have many new applications that have come up which demand a lot of bandwidth and a lot of speed from the internet. Okay. So with the growth and the evolution of the internet, what has also happened is there is a need to evolve the routing algorithms, there is a need for an advanced and efficient forwarding algorithm. And if you look at routing versus the switching debate, routing will give you flexibility, forwarding will give you price per performance. So how do I get something like the best of both? I want some flexibility, at the same time I want to have good performance as well. So can we forward or switch IP packets? So that question also has to be answered. So we need to understand this debate correctly and take advantage of the techniques that are there in both the mechanisms. Okay. So ideally what we would like to do is we would like to have the speed of L2 switching at L3. That layer 2, if you have layer 2 switches, you know that they switch at a very fast rate, right. So you would like to ideally have that kind of switching at L3 as well, right. And so to make that happen, what we would actually like to do is that if the router can make the L3 forwarding decision based on a single field, okay, it would definitely give rise to a good amount of speed. So how do we do that? So that is the further motivation for MPLS, for an MPLS kind of technique to have evolved as such. Okay. In fact, the original drivers towards label switching actually came from the ATM world. Okay. The asynchronous transfer mode, which was proposed earlier as a virtual circuit switching mechanism, was originally designed to make routers faster. So ATM switches were faster than routers, primarily because they used a fixed length label lookup. They used what is called as a cell, which had fixed size headers, and it was very easy to process them because they were all a fixed size. Okay. So faster, so it was much faster than a longest match that is used by the IP routing. So the original motivation for MPLS basically came from trying to use ATM kind of devices or ATM devices as such along with the IP world, right. So, the IP networks. So, how do we combine these two? So, that is where MPLS was originally thought about. So, in a sense it is basically trying to get the best of both worlds, right. So, MPLS plus IP should form a middle ground that combines the best of the IP and the best of the circuit switching technologies. So, if I have packet switching IP at one end and ATM kind of circuit switching at the other end, what we are trying to do is try to get somewhere in the middle a hybrid technique which uses MPLS plus IP. So, you are trying to get something done along with IP in order to go towards the speed and performance of circuit switching machines. So, that is the idea of this multi-protocol label switching protocol. So, essentially if you look at MPLS, what does it do? It is a protocol to establish an end-to-end path from the source to the destination. Plus it uses a hop by hop forwarding mechanism, okay, as we do in the case of the IP packets. Okay. And to set up this path, it basically makes use of labels. Okay. So, since it uses labels to set up the path, you would also require a protocol to set up the labels along the path. So, it also includes a label kind of based label distribution protocol. Okay. And it builds a connection oriented service on the IP network. So, that is the basic idea. Okay. And where exactly does this MPLS protocol reside? You can say that it comes somewhere in between layer 2 and layer 3. In fact, MPLS is also referred to as a layer 2.5 protocol, which means it comes in between the layer 2 and layer 3. Okay. So, if you look at the characteristics of MPLS, basically there are mechanisms to manage traffic flows of various granularities. So, some kind of flow management is widely supported, and it is independent of the layer 2 and layer 3 protocols, which means it can work with a variety of layer 2 protocols and layer 3 protocols. Okay. So, what it essentially does is it maps the IP addresses to fixed length labels, and it interfaces to existing routing protocols such as RSVP, OSPF and so on. Okay, and it supports ATM, frame relay and Ethernet at layer 2. So, you can see that it kind of works with number of protocols, and which is where it gets this name of multi-protocol label switching. So, it can work with multiple protocols as well. Okay. So, some terminology that we need to understand with respect to MPLS. We talk about LSR or label switch routers. So, these are routers that support MPLS. So, they are called as label switch routers. Then we talk about LER or label edge routers. Now, these LERs are essentially label switch routers, but they are at the edge of a network. Okay. So, we talk about an ingress LER. So, ingress LER is one which is there at the incoming end of the network of the MPLS network. Okay, and this is responsible for adding labels to the unlabeled IP packets. That is, when an IP packet is sent into an MPLS domain, it will first go to an edge router. So, that edge router is an ingress LER. So, that LER is responsible for adding labels to the unlabeled IP packet. Similarly, when it exits the MPLS domain, when a packet exits the MPLS domain, you will have a LSR there, okay, and an edge router there, an LER, which will act as the egress LER, and this will be responsible for removing the labels, because what has to be sent out will have to be an IP packet without these labels attached to it. Then we talk about something called an LSP or a label switch path. Now, this label switch path is the path which is defined by the labels through the LSRs between the two LERs. Okay, there is one ingress LER and one egress LER. The path that exists between these two is called as the label switch path, and it is essentially defined by the labels. Then we also have a label forwarding information base. This is it's like a forwarding table or a mapping which provides the mapping between the labels and the outgoing interfaces. So, if I get a packet with this particular label, which is the interface that needs to be sent out on. So, that is the kind of forwarding information base that you have. So, another concept associated with MPLS is what is called as FEC or forward equivalent class. Okay. Now, this forward equivalent class is a concept that is used to group packets which need to receive the same kind of treatment. Okay. So, all IP packets which belong to a particular forward equivalent class will follow the same path on the MPLS network, and they will receive the same treatment at each node. So, this gives us a mechanism to group packets, okay, and give them a similar kind of performance. So, how does this whole thing work? So, as I said, you have an LER at the two ends and maybe multiple LSRs in between. Okay. So, this LER is our ingress LER. This is responsible for adding label to the packet, and this LER is responsible for removing the label from the packets. So, once an IP packet comes in, this is what will happen. So, IP packet comes in, this is added the label L1, At these intermediate LSRs, so what will happen is something called label switching. So one label may be replaced by another label. So L1 is replaced by L2 and sent along to this LSR. So this LSR replaces L2 with L3 and sends it to this LER. This egress LER removes the label and sends it out as an IP packet as such. Okay, so this is basically how the data will flow through the MPLS network. So what is this label? So this label actually is a simple integer which identifies an FEC or a flow. Now it is very difficult to have globally unique or network unique labels. So what we normally do is we use link level labels, that is the labels are unique only between two nodes. Okay. And the labels will change at each node as a packet traverses the path. Okay. We just saw how that is done. Okay. You can set labels manually, which is very cumbersome, or you can use what is called as a label distribution protocol. So this is what is normally used. Just to give an example of a label forwarding information base, this is what it will look like. So you have an interface on which it will come in with a particular label. This may be its actual destination address, and it will go out on this interface with a label of 40. So it comes in with a label of 50, goes with a label of 40, right. So that's the kind of information that you will have in this label forwarding information base. So all that you need to do when a packet comes in is look at this table, look for this label, change that label to this value, send it out on this particular interface. So that's a simple process, and that gives this speed for processing the packet. Okay. So if you look at the label a little deeper, so you will see that it has a 20-bit label field, that label value which is actually used for as the pointer for forwarding. Plus there are 3 bits which are used for experimental purposes, often this is used for quality of service purposes. And then there is something called a 1-bit stack field, a bottom of stack flag that is used. So what this basically indicates is that you can actually have multiple labels attached to a particular packet. That is, if it is being forwarded through multiple paths, you can actually have multiple labels added to it. But you would normally be looking at only one of those labels, right? So you need to know whether there are a stack of labels or whether there is only one label. So this bit here will tell you whether you are at the bottom of the stack or there are other labels which are sitting on top of it. Okay. So one indicates that no label follows. So this field is useful for you to process these labels. Okay. So you know whether you need to process it further or whether you need to remove the label or whatever you need to do with the particular label. Okay. And then there is an 8-bit TTL field, time to live field, which is very similar to that of an IP packet. So treated almost the same way as the IP packet is done. So in terms of how this label is encapsulated, where exactly this label is stored, if you look at for different L2 layer protocols, the label is handled in different manners. So if your L2 protocol is ATM, if you are working with ATM, then ATM actually has a VPI and VCI field. So these fields themselves are used as the label. Okay. The label basically is used in the place of these VPI, VCI fields. If it is frame relay protocol at L2 layer, there is a DLCI field that is available in frame relay protocol, that is used as the label. But if it is Ethernet or PPP protocols that are used at L2 layer, now there is no provision for any additional information to be or anything to be kind of overlaid over here. So what we do here is we use what is called as a shim label. So a shim label is something which is inserted between L2 and L3 layers. Okay, so you have the Ethernet header here and you have the IP header here. So L2 header here and L3 header here, and this is where this label is inserted, the MPLS label is inserted. So it is called as a shim header. Okay. So this is basically how the MPLS will be encapsulated when you are using Ethernet and IP. Okay. And how is this label distributed? Okay. Now MPLS has actually multiple methods for label distribution. One is that you could use BGP to itself, and BGP itself has been enhanced to carry label information. That is one option. There is also RSVP protocol has been extended to support the exchange of labels. Plus there is a new protocol called the label distribution protocol, which is used for explicit signaling and management in MPLS networks. Okay. And there are also extensions to the basic LDP protocol in order to support explicit routing based on QoS requirements. So you have a lot of support for QoS routing which are provided as part of the LDP protocol and therefore as part of the MPLS protocol as well. Okay. So the label edge router that we talked about, right, we said it is the one which will reside at the edge of an MPLS network and is responsible for assigning and removing the labels from the packets. Okay. And it also supports multiple ports connected to dissimilar networks, for instance frame relay, ATM, Ethernet and so on. And the LSR, the label switching router, as we said, it's a high speed router in the core or on an MPLS network. And what is interesting is that ATM switches themselves can be used as LSRs without changing their hardware. Okay. So label switching then becomes equivalent to VPVC switching. So this is, you will see, one of the major reasons, as we talked about earlier, as to why MPLS was thought of in the first place, that you wanted to use the ATM infrastructure as such. So you can see exactly what will happen over here. So you can see that a IP packet comes in with a particular comes in over here from the Ethernet. This is the Ethernet header, this is your IP header. Now at the LER here, the between the Ethernet header and the IP header, a label is inserted. Let's say L is equal to 5. So now how does the L5 inserted? That is done by looking at the forwarding table where you have IP address and the out label which is specified here. Now when the packet comes here at this LSR, at the LSR we do what is called as label swapping. So 5 is changed to 9, replaced with 9. Okay, and similarly at the next router again 9 is replaced with 2. So in label and out label are available in your forwarding base. So looking at that, you do this do the label swapping, and at the egress router at this LER you are removing the label and you send it out. So this is, so what we are essentially talking about is do the routing at the edge, switching in the core. So what do I mean by routing at the edge? Based on the IP layer header, whatever should be the label attached, okay, what is the FEC that should be specified for this packet? All the decision of classification, whatever you want to do, is done at the edge, okay, so which is why we say route at the edge, and in between we just do a simple job of switching, just switch the labels. So this forward equivalence class, or FEC, is the core of this entire MPLS protocol. So what this actually tells us is that it gives us a representation of a group of packets that share the same requirements for their transport. And the assignment of a particular packet to a particular FEC is done just once, that is when the packet enters the network. So for instance, if you have, for instance, 2 packets IP1 and IP2, they are actually meant for 2 different destinations, but let's say they require the same kind of treatment, okay. That is, they can be mapped to the same common path. Their address prefixes are different, but we would like them to go through the same common path. So what do? We assign both of them the same label. Okay, IP1 is also assigned the label L1, IP2 is also assigned the label L1 based on the fact that their forwarding equivalence classes are the same. Okay, they need to be forwarded in the same manner. So you can see that this L1 now will get switched to L2 at the next router, to L3 at the next router, okay, and then finally from here at the egress LER, they will be sent on their respective paths depending on what the IP header information is. Okay, remember that the edge router will look at the IP information. So based on that, it will be able to send it on the correct path. So inside they will be given the same treatment, outside they can go their own way. Okay, that's the idea. Okay, so it will go to IP1 and IP2 here. So if you take an example with, let's say I have routers, R1, R2, R3, R4. Okay, so if you look at how exactly the information will be stored in the label forwarding information base. So R1 will have an incoming label as nil. Incoming interface E0, which is the destination network, which is the FEC. So based on that, the outgoing interface is set out as S1, the label is 6. At R2, incoming label will be 6, so that you can match this with this, right? So incoming label is 6, outgoing label will be 11. At R3, incoming label is 11, outgoing label is 7. At R4, incoming label is 7, outgoing label is nil, because there is no, the label is removed over here. So if you look at what is happening in along the label switch path, you can see that at the ingress node, what happens actually is a classification, label assignment, everything gets done. You look at the LFIB and do all the necessary label assignment. At the core nodes, only label switching is done, right? Only label swapping is done. And at the egress node again, label removal is done. Okay, here again the LFIB will be contacted. Okay, so this is basically what happens. Okay, so this label switched paths that we talked about, LSPs, right? So when exactly is this path established? Obviously it has to be established before the data transmission starts. So a path, you can say, is a representation of an FEC. Okay, so if you look at how the LSP is set up, right? So MPLS actually provides 2 options to set it up. Okay, one is called the hop by hop routing. So here each LSR independently selects the next hop for a given FEC. Okay. So LSRs support many available routing protocols, OSPF, ATM, so on. So they can use that information and set up the path. The other is explicit routing. This is actually similar to source routing. So in this, what happens is that the ingress LSR will specify the list of nodes through which the packet should traverse. Okay, so this is very similar to the source routing mechanism. Okay. And the LSP which is set up for an FEC is unidirectional, which means for the return traffic you will have to set up another LSP, and it can also take another LSP. A different path can be taken for downward traffic rather than upward traffic. So to take an example, so let's say we have, let's look at IP based forwarding used by the hop by hop control. So what will happen? So essentially you will have if a packet is meant for 47.1.1, by looking at the interface, output interface that's there in the table, it will be sent on that particular interface. So again a packet lookup, a table lookup will be done, it will be sent on the corresponding interface. Again a packet lookup, a table lookup, and the packet is sent on the corresponding interface. So this is what normally happens, right? Now for label distribution to take place, let's look at what will happen. So when the packet arrives, okay, or before the data can be transmitted, so what is actually done is a request for sending packets meant for 47.1 is sent over here. So this is basically a request for labels for sending data to this particular node 47.1. So now what this router will do is it will forward this request towards the destination. So this router, the edge router which is connected to 47.1, receives this, and now what this will do is it will now make an entry in its table. It says, okay, so if I am getting a packet which is destined for 47.1.1 which comes in on this interface, I know I have to send it out on interface 1, and the label I will assign for this is 40. So which means this information now will be conveyed by this router to its downstream router, right? So now this will send a mapping saying, mapping that I am giving you is 40. For this FEC that you sent, request that you sent, the mapping is 40. So now what this router here will do is make an entry saying, if I get something with a label of 40, if I get a packet, I have to assign it a label. So it will assign a new label of 50 and say that if I get a label with packet with a label of 50, I will be sending it out with a label of 40, and that is the entry that it makes over here. So 40 is something it got from its upstream router, and now it assigns a label for its downstream traffic. Okay, so for this path the label is assigned by the upstream router. Okay, so you can see this. So now this fellow now assigns the label as 50, and now he will send this information to the router downstream. The downstream router now will make its entry saying, if I get something on interface 3 with this destination, I will send it out on interface 1 with the output label of 50. So once this is done, now you can see that the path that is required is set up. Okay, so with the path set up now, so you can see this. So if it comes in with a label of if it is destined for this particular 47.1, it will be sent out on this interface 1 with a label of 50. So it goes here, from 50 it will be converted, it will be swapped to 40, here it will be converted, it will be, it receives a label of 40, so it will be sent out on interface 1 after removing the label. Okay, so this is what will be set up over here. So when a packet comes in, it just is directly sent along this path and is sent out. Now talking about the label distribution protocol, we said that there is an LDP protocol that is provided. So this is actually an application layer protocol for distribution of the label binding information to LSRs. So it is used to map FECs to labels, which in turn create the LSPs. Okay. So the LDP sessions, as they are called, okay, are established between LDP peers in an MPLS network, not necessarily adjacent. It can also talk to other routers which are 1 or 2 hops away from it, and it sometimes employs OSPF for BGP as well. Okay. So LDP protocol, if you look at the different types of messages that are there in LDP, you have what are called as discovery messages, session messages, advertisement messages, and notification messages. So the discovery message is basically to announce the presence of an LSR in a network and maintain the presence of an LSR network. So you keep announcing periodically to indicate that I am alive. Okay, that's kind of a message that you have. Session messages are the ones that are used to establish, maintain, and terminate sessions between LDP peers. So you will have to start a session, maintain the session, and close the session. Okay, that is how you do that. Advertisement messages are the ones that are used to create, change, and delete label mappings for FECs. Okay. And notification messages are used for advisory information, signal error information, and so on. And there are 2 label advertisement modes that are available. One is called the downstream on demand mode, okay, and another is called the downstream unsolicited mode. Okay. Now what the downstream on demand indicates is that once it receives, when an upstream router receives a request for binding from a downstream router, then it will send the label FEC binding for it. Okay, that's called on demand. Only when it requires, when it gets a request, it will send the mapping. Downstream unsolicited says that even without the downstream router asking for it, not soliciting information, the label FEC binding will be sent by the upstream router to the downstream router. Similarly, there are also two label distribution control modes. So what we mean by this is that something called an independent mode, and then we have something called an ordered mode. So in the independent mode, an LSR can notify label binding messages upstream anytime. Okay. Whereas in ordered, an LSR can send label binding messages about a FEC upstream only when it receives a specific label binding message from the next hop for a FEC, or the LSR itself is the egress node of the FEC. Okay. So this ordered is that only on receiving something from somebody else it will trigger a message to be sent. In independent, can send it at any point of time. Okay. Similarly, we also have something called a label retention mode, which talks about how long do you have to keep holding that label. So we have something called a liberal mode. So in the liberal mode, the LSR keeps any received label to FEC binding, regardless of whether the binding is from its next hop for the FEC or not. Wherever it comes from, it will hold on to it. Conservative is it will only keep those labels which come from its next hop for that corresponding FEC. In the liberal mode, the advantage is that the LSR can adapt to route changes quickly because it is receiving it from various places. Okay. But in the conservative mode, there are less LEC to FEC bindings for an LSR to advertise and keeps. That will be its advantage. The conservative mode you can see is normally used with the DOD mode, that is the downstream on demand mode, okay, in order to maintain the limited label space. Okay. So you can see. So if you see this, for instance, the dotted lines here actually indicate paths which are not exactly on the FEC path, okay, but still if they advertise certain labels, those labels are just kept. Why does it keep those labels? So that in case of failure, say this something happens and some other LSP fails, it will be able to quickly switch over to another LSP. So that is the advantage of having this kind of a liberal retention mode that we have. Now if you look at the applications of MPLS, there are three major applications. One is traffic engineering, another is to set up virtual private networks or VPNs, and the third is to provide quality of service. These are three applications for which MPLS has been very vigorously used these days. So to engineering essentially is giving control to the network administrator to provide whatever controls he wants, to provide, to bypass the normal routed hop by hop paths, make some deterministic routing, all those things you would like to support. So that is something that we normally need in order to provide the quality of service that is required by certain customers. So an administrator may elect to explicitly define the path between stations to ensure QoS, right, or have the traffic follow a specified path in order to reduce the traffic loading across certain hops. Now these are all things that are part of traffic engineering. Administrator may want to do all these things. Okay. Similarly, to handle congestion and to force the frame to travel around overloaded segments, that's also something that comes under the purview of traffic engineering. Now these things can be easily supported with the help of MPLS. Okay. So how is that done? Okay. So you can see, for example, so let's say these two are overloaded. Okay. Now this is the normal path. So what is it that we can do? You can set up a path which says forward to LSR 2, 3, 4 and X. So once I have a IP packet coming in, it's forwarded to LSR 2, right, and then through to from LSR 2 to LSR 3 and then from there to LSR 4. So an alternate path is taken when this is overloaded. Okay. So this end-to-end forwarding decision is made at the ingress node. Okay. So the ingress node therefore can make this switch, and it will help to support traffic engineering by choosing alternate paths. And for MPLS based virtual private networks, the basic concept is similar to what happens in ATM LANs as well. Let us not worry about that. So what we are actually doing here is that we are using labels instead of IP address to interconnect the multiple sites over a carrier's network. So each site can have its own private IP address space, but using labels you will be able to connect them up. So different VPNs may use the same IP address space. That is also possible, right. So if you take for instance a model like this, I have two nodes here connected to the same site, okay, which this belongs to VPN A, to a virtual private network A, and this belongs to VPN B. Similarly, let's say the yellow ones and the green ones, right. So yellow ones belong to a particular network, the green one belongs to another VPN. Okay. So now depending on, by providing different labels, you can connect up this network only to the yellow ones, only to the yellow ones over here, and the green ones only to the green ones over here. The paths can be set up accordingly, right. So, that is the that is how you can use label switching to support virtual private networks. Okay. The IP addresses may be anything, but because across this network we only have labels that are used to identify the packets coming from there, you can actually set up the network the way you want. So, for instance, if I want packets from here to be forwarded to this, right. So, what do? At E1 I will say if it is coming from 192.168.1.0, I set up a path which says if it is from E1 10, go out on E3, right. At this router I say it comes with the label of 10, send it out to the label of 30. Here I will say if it comes to the label of 30, you send it over on this path. So, I have a path for this. Similarly, coming from here I can route it to this route here, that is connect only these two as part of a same network by saying having a different label for this. So, this is label is 20. So, it comes with the label of 20, it goes to the label of 40. If it comes to the label of 40 here, it goes to this particular network, right. So, one path along this direction and similar LSP on the in the reverse direction can be set up for connecting up this virtual private network. And in order to support quality of service, a number of things can be done. You can classify the incoming packets into different classes, okay, and this can be done at the ingress routers. So, you can assign a label which is corresponding to the resultant class. The classification can be made on various characters. You could use congestion, throughput, delay, loss, whatever, right. And the labeled packets are handled by LSRs in their path without needing to be reclassified. So, all classification will be done at the edge router, no classification at the intermediate routers, they just keep forwarding it, okay. So, MPLS therefore gives you a simple logic to find the state that identifies how the packet should be scheduled, okay, and it can support various other QoS protocols such as INTSERV, DiffServ, RSVP and so on. In fact, we have DiffServ working with MPLS as one of the very commonly used protocols in many of the networks today. So, the FEC QoS classification can be done on various parameters. It could be done based on the physical interface, source IP address, destination IP address, type of service field, protocol information, etc. And all this is done at the LER. Once it comes into the MPLS network, it is only based on the LSP and that is determined only by the label. Okay. So, you can have support for QoS as well. Okay. So, the another option, for instance, you could use the type of service field that we have in IP. That can be used to set the label appropriately. So, your IP precedence bits, okay, whatever bits you have in the TOS fields, they can be used to set the label and therefore, you can provide the required quality of service. Okay. So, operationally for MPLS to work, these are the following things that will have to be done. Okay. First is you will have to create labels and distribute them. So, that will help to set up the LSPs. Then table creation has to happen at each router. And then a label switched path will have to be created. Label insertion and table lookup will have to be done as the packet comes in, that is at the ingress labels have to be inserted and table lookup will have to be done at all the intermediate routers, and of course label removal has to be done at the egress router and packet forwarding is to be done at each of the intermediate LSRs, right. So, these are the basic terms that or the basic steps that we need to remember as far as routing within MPLS domain is concerned. So, advantages of MPLS are that it improves packet forwarding performance in the network, supports QoS for service differentiation, supports network scalability, integrates IPM and ATM in the network, basically builds interoperable networks. Okay. So, that is the reason for MPLS becoming very popular these days. So, to summarize, we have looked at the basic idea of MPLS, the terminology associated with that, its architecture and its components and some of the applications of MPLS. Thank you.